Okay, here's a lesson we're dealing with year 12 probably in circular motion. And it's a really important topic area because it's the grounding which you have before you carry on to study subjects like simple harmonic motion or any wave theory. You need to get to grips with the ideas of circular motion. So I'll start with you with a simple problem which you might be able to solve yourselves before we introduce the new ideas. Here's a terribly uncircular bike wheel, and I've got spokes that are supporting that bike wheel. Let's say, for argument's sake, that we do let's say we do 48 revs per minute, RPM, and the radius of the bike spoke is 0.5 meters. Now, if I was to ask you how fast is the spoke moving, then I'm sure you would all have a pretty good attempt at trying to work out how fast the spoke is moving. You would probably say something like, you would work out the circumference of the wheel, you'd divide it by how long it takes for one revolution, the time period of the revolution, and that will come out with a velocity. And you wouldn't be wrong in saying that, and you're correct. However, what you would be working out, of course, is the velocity at the top of that spoke. However, halfway down, the spoke is actually moving at a much reduced velocity, and a third of the way, again, a much reduced velocity, because each of these potential points has a shorter circumference to have to go around. So that which you were hypothesizing was probably the velocity at the very end of the spoke. So what property do we have that can actually be classed as constant for any part of that spoke as we move from one to the other? And I suppose the property that we can talk about is how many angles this spoke has cut through in a given time period. So in other words, though this may vary, the number of angles cut through each second is going to be constant for every part of that one spoke in question. So therefore, let's try and work this out. And by the way, the number of angles cut through each second we call omega, or, if you like, the angular velocity. So what I suggest to you now is you have a go. Well, let's work out the angular velocity of this one spoke as it flies around. If you think you know the answer from the data above, then hit pause and give it a go. Otherwise, here comes the answer. Okay, so angular velocity is going to be the number of angles cut through per second. So I know I'm going through 48 revolutions, of which we have 360 degrees per revolution, and I know that's happening in 60 seconds because it's 1 minute. Now, let me just send that on. I'll just type it into the calculator to make absolutely sure about the numbers, and that gives us 288 degrees per second. So if I were to let 1 second to elapse, then I'd go through 288 degrees. Not that far off there, probably. Okay, but it's not really that useful to talk about things in degrees per second. It's much easier to talk about things in radians per second. So what would this be if we had it in radians per second? Well, very simply, what we would do is rather than using 360 degrees, we'd use the number of radians in one complete revolution, which is 2 pi. So if we plug that number in, we come out with a nice one of 5 radians per second. In other words, what we're looking for is a good appreciation of this idea that omega is the number of revolutions divided by the time period. And it's measured in radians per second. Now, interestingly here as well, we have an expression for velocity up here, which is 2 pi over t times r. So therefore, if I were to multiply omega by the radius of whatever point I'm dealing with, that gives me the velocity. Omega, angular velocity times radius, is the radial velocity. That's the word I'm looking for, the radial velocity. Let's just make sure it all works. Rads per second by meters gives us meters per second. Good, so let's start to hold that into our minds, and especially this concept here. Right, let's find some examples, and we can give them a go. So, dealt with the spoke. Now let's deal with the Earth. Whoops, too many sheets of paper here. Let's deal with the Earth of radius 64,000 kilometers. And the question is, what is the angular velocity of the Earth? And what's the velocity on the surface of the Earth? So if you think you know the answers, hit pause and give them a go. Otherwise, here comes the answers. Okay, very simply, the number of angles cut out per second. Well, you know that the Earth does one revolution in 24 hours, which is 24 times 60 seconds. And that gives a grand total of, as memory serves, it's going to give us, let me just type it into the calculator, divided by 60, 24, 7.3 times 10 to the minus 5 radians per second. Sorry, that's written very, very small there. So what's the velocity of the Earth? Let me write it down here so we can see it a little better. Well, we know it's omega times r, which is the same as saying 7.3 times 10 to the minus 5 by 6400. Remember, it's in kilometers, giving us a grand total of 465 meters per second. So the surface of the Earth at this point here moves around 465 meters per second, with it rushing around at 7.3 times 10 to the minus 5 radians per second. Okay, let's move out towards the Moon. What is omega of the Moon if the radius here is approximately 300,000 kilometers? What is omega of the Moon, and what is about the Earth? What is the velocity of the Moon about Earth? And then finally, what's omega of the Moon moving around? Right, if you think you're moving around itself. Right, if you think you know the answers, hit pause, otherwise here comes the solutions. Okay, the Moon. So the one complete revolution of the Moon goes around in one Earth month, which gives us this number of seconds. Okay, so that gives us, divided by a day, divided by number of seconds an hour, 2.6 times 10 to the minus 6 radians per second. Therefore, the velocity, omega r, is going to be 2.6 times 10 to the minus 6 times by 300,000 kilometers, giving us 80 meters per second. Screaming around faster than the speed of sound. What about omega of the Moon? Well, this is a really interesting one. There's a quick way of getting the answer here. the moon goes around the Earth. So let's imagine this is the point. So as it moves to another position, so the moon turns at the same rate about its axis as it does about the Earth. So it always faces one side permanently to the Earth. There's always a dark side to the moon. They never saw this until they went around on the moon landings. So therefore the omega of the moon is going to be the same as it around the Earth. Okay, we could expand this again and say, okay, right, what do we have if we have the Sun? And we know that this is 8.5 light minutes, which is the radius. It takes light 8.5 minutes to go from the Earth to the Sun. So what is omega of the Earth about the Sun, and the velocity of Earth about the Sun? Think you know the answers? Hit pause. Otherwise, here comes the solution. Okay, the angular velocity is going to be the 1 full revolution divided by 365.25, the number of days in a year, because it rotates around once a year, giving us, in radians per second, it's going to be times 10 probably. A bit of a squeeze there for the answers, but divided by 24. Okay, so 2 times 10 to the minus 7 radians per second. That's how many radians the Earth is moving about the Sun. What about the velocity? Well, you notice omega r, which is 2 times 10 to the minus 7 omega times 8.5 minutes, convert it to seconds, and convert it by the number of meters per second, i.e. the speed of light. And that gives us a grand total of 30,000. Near enough, 30,500 meters per second. Approximately 31 kilometers per second. Okay, so hopefully we've got a good understanding of omega, angular velocity, and how angular velocity relates to radial velocities. Excellent. Okay, we're not quite done there because we need to now look at, if we have our speeds, we now need to look at our accelerations. So let's just remind ourselves of what's happening here. So omega and velocity. Acceleration, so the velocity is equal to, acceleration is a change in velocity divided by change in the time. Acceleration, of course, is equal, velocity, of course, is equal to the change in distance divided by the change in time, which in this case gives us omega r. Omega, of course, is 2 pi over t. And any movement that moves from one side to the other side just requires a multiplication of the radius. Acceleration is the rate of change of velocity with time. So what we need to do is we need to find something similar, an angular acceleration, and then relate that to the real acceleration. So here comes a little proof. Here is my circle, and here are, at 2 points, the velocities. Now, the magnitude, i.e. the speeds of these two are equal. But of course they're pointing in different directions. They've gone through an angle of theta, and there has been a change in velocity it's undergone. This vector has been changed into that vector. So let me just draw these two vectors. That's the change that I've experienced. Here's v1 and here's v2. with the same angle between them. So this is a sense of velocities. It's one identity. And now what we need to do is work out, well, what's the actual distance going on here? What's this distance s if this is of length r from the centre? And what we can say to ourselves is, actually this is simple circle formula theorem, theta is s over r. And if angles are very small, we can say that s is approximately the same. S is the same as the distance travelled around the circle. Let's say s dash around the circle. Okay, good. So now we've got an expression for theta here. Similarly, in this identity here, my theta is going to be, in the same way that it was this divided by that in circle theorem, it's the same angle, so therefore it's going to be delta v divided by v. No, those two are equal. Good. So, where do we go from here? Let's say the distance is going to be whatever velocity, speed they're travelling at, multiplied by the time it takes them to traverse around this number of angles. So therefore, v multiplied by the change in time required. I mean, hopefully the change in time is very small, divided by r. We also know that v is delta v divided by v from this identity. So this side is from part 1, and this side is from part 2. So what does that leave us with? Well, it says delta v over v is v delta t over r. Let's just change it a little bit. So we do delta v over delta t gives me, I move this down, I move that up, v squared divided by r, which is the same as the acceleration. Good. So this is equal to v squared divided by r. We can also say, if I replaced in there velocity is omega r, all squared, divided by r, that gives us omega squared r is the acceleration. Okay. And as I said, if we move from here to here, we multiply by r, the v squared over r squared must be our angular speed, or even omega squared r squared over r squared which leaves us with the change in r over the omega over the change in t. This is angular velocity, so actually ignore that proof. Oops. That a number of angles that are speeding up, how many angles they're cutting through, is increasing by the rate of change over time. Okay, let me just put a proviso. This bit here, though I wanted to show the entire similarity between the two, is probably not needed for your work for PH4. It will be needed for PH5 option, but not PH4. However, this is very important. This is exceptionally important. And those analogies are very, very important as well. Okay, let's give one more example. Now we've got those in mind. Let's go to thinking about CERN. You've got the particles are flying around a 27 kilometre ring. That's the circumference. Let's say they're approximately going at speed of light. Three times 10 to the 8. I want to know the angular speed of those electrons or protons, depending on whether it was the LHC or the LEP. I want to know the acceleration, the angular acceleration required to keep those going around in a circle. So angular velocity and the acceleration. If you think you know how to do it, hit pause. Otherwise, here comes the answers. Okay, now, angular acceleration, angular velocity, is 2 pi divided by t. But what we don't know yet is the time period. So we can either say, work out the time period before this, saying, I know we've got 27 kilometers divided by the speed of light, giving us 9 times 10 to the minus 5 of a second, and we can work that through. Or indeed, I can say we have v divided by r, velocity divided by the radius. Similarly with the angular acceleration, we can either say, well, I've got v squared divided by r, have v and infinity divided by r, or indeed we have omega squared multiplied by r. But either way, we need to find some value for r. So I've got a time period. Now r is going to be the circumference divided by 2 pi. That's just a big C, circumference divided by 2 pi, which gives me 27 times 10 to the 3 over 2 pi, which gives me just click something wrong on the calculator, 4.3 kilometers. Okay, so knowing what we know now, let's go and work out omega. Let's go 2 pi over t, because that's a really useful, you'll come across that all the time. So let's just type that in. Okay. So we get approximately 7 times 10 to the 5 radians per second. The acceleration is going to be v squared over r, or even omega squared multiplied by r. So let's square that function, multiply by r, and that gives us, so let me just write that down as a squared function. And instantly see we're up to something like 10 to the 13 meters per second squared. It's a huge change of momentum, huge acceleration, but it needs to be to correct these parts as they go around. Okay, so I hope that makes sense.